Hello, everyone. Welcome to another virtual time series seminar. Today we have Andrii Babii with an interesting paper on tensor principal component analysis. We also have two guest panelists, Mirco Rubin and Zheng. If you have any questions at any point in time during the talk, please just ask your question, or if you prefer, you can write in the chat. Thank you and enjoy your seminar. Andrii, the floor is yours.
Okay, so thank you very much for the invitation. This is a joint work with my colleague Eric Geisels and a graduate student, Zheng Pan, who is on the market this year, and yeah, so he is a great student. Okay, so here's the plan for the talk. First, I will describe a tensor factor model. Second, I will talk about the estimators that we use in this paper, which we call tensor principal component analysis. I'll present some supporting asymptotic theory for these estimators and for a test for the number of factors, some Monte Carlo experiments, and an empirical application to asset pricing, namely sorted portfolios. So what is a tensor? A tensor is basically a multidimensional panel data set. So this is a multidimensional array that generalizes vectors and matrices to higher dimensions. Here we have, for example, a scalar, a vector, a matrix, and if you put several matrices together, we get a three-dimensional tensor, and then we can keep going, put several three-dimensional tensors together and get a high-dimensional fourth-order tensor. So this kind of data is very often encountered in the empirical practice. For example, in macro applications, we can have a panel of macro indicators observed over time, and we have this extra third dimension, which is a region. We can also, we can also consider, for example, sales data. So we have a panel of firms that sell different products at different points of time, or financial data. So in our application, YIJT would be the excess return on a J's quantile portfolio sorted on I's characteristic time t. So despite the fact that tensor data is very often encountered in the empirical practice mostly ignores this tensor structure. And usually the structure is reduced to panel data, and standard panel data methods are applied. So this paper tries to apply insights from the PCA literature to tensors and tries to explore better these extra tensor dimensions that we have. We have PCA type estimators for d-dimensional tensors of panel data. Our other contribution is to develop the first test for the number of latent factors in tensor factor models. And we offer something that is super easy to use. We have closed form expressions for estimators, and we don't have to solve any complicated non-convex optimization problems. So tensor factor model. I'll introduce the tensor factor model. Before doing that, we will look at a simple two-dimensional factor model. So in a classical two-dimensional factor model, we are trying to explain some panel, YIT, I is the cross-section, T is time. And we want to explain the dependencies that we have in this panel, the cross-sectional dependence and time series dependence, using some small number of latent factors denoted by F. And each factor has a corresponding latent coefficient, which we denote by lambda. So in the asset price application, we could have YIT, which is the excess return on the asset I at time t, and we try to capture the co-movement of asset returns using a small number of latent factors. If we put the model in the matrix notation, so we can collect these data into a matrix, and then in the left side we have n times t matrix denoted by y. So we stack all cross-sectional units over time. And in the right side of this equation, we have a sum of rank 1 matrices. So we have R rank 1 matrices, and here lambda is a vector. It's an n-dimensional vector corresponding to all loadings. F is a time series vector, t-dimensional vector corresponding to the time dimension. And we use this notation, tensor product, which is just an outer product of two vectors. So the objective here is to identify the latent factors F and the corresponding loadings lambda, and they tell us about the exposure of different cross-sectional units to time series factors. So factor models are used everywhere in economics and finance. In addition to asset pricing, these models can be used to analyze business cycle, forecast with big data. In the consumer theory, theoretical considerations also give us low-rank structure. Also, in the empirical practice, people very often use two-way fixed effects models. So we have panel data, and we add cross-sectional fixed effect and time series fixed effect to capture heterogeneity. The issue is that model is that it doesn't allow us to have time-varying heterogeneity. And so there is large literature on interactive fixed effects that allow us to capture time-varying unobserved heterogeneity, and also causal inference with panel data. So now we generalize this model to the three-dimensional case. So we work with tensor data. We have this extra dimension denoted by j, and we have a loading mu j, which is the loading of this third dimension on each factor. And like before, we can collect the data set into a matrix form. We denote this matrix by y. And in the right side, we have a tensor product of three vectors, and we have R such tensor products summed together. So this is how this looks graphically. And basically, this means that each component of this three-dimensional cube can be represented in this way. So this procedure, this model can also be generalized to the d-dimensional case. We just have a Messier notation, and it is convenient to use this shorthand notation. So the d-dimensional tensor with dimensions n1 and 2 until nd is explained as a sum of R rank 1 tensors, and a rank 1 tensor is just an outer product of d vectors. So this is related to what is called the canonical polyadic decomposition, or CP decomposition, but we are looking at the model, so it's a factor model. So next, of course, we cannot identify the scale components in this model, and we will do some normalizations. So we will focus on identifying unit norm factors and loadings denoted by M. Depending on the dimension j, this M can correspond to a factor or to one of the loadings for other dimensions. So these are unit norm vectors. And we also have the scale component, sigma r, which absorbs the scale of all factors and loadings. So this is going to be the product of norms of factors and loadings across all dimensions. And we can have interpretation for this sigma as a signal strength. So large sigma means that we have a stronger factor. Smaller sigma means that we have a weaker factor. And our objective is to identify these unit norm factors and loadings, as well as the corresponding scale components. So next, I'll talk about the Tensor PCA procedure. So in the two-dimensional case, what PCA tries to do, it tries to find linear combinations of variables, so directions in the multi-dimensional space where we have most of the variation of the data. So here on this scatter plot, we see that most of the variation happens along this dimension. So this is the direction for the first principal component, and then we have the remaining orthogonal second principal component. And mathematically, we can describe this procedure as follows. So we are trying to maximize the variation in the data, subject to the fact that directions are unit norm vectors, and they are also orthogonal. And we know that this problem can be solved using the eigendecomposition of the sample covariance matrix. So we take the sample covariance matrix y transpose y, and we look at our leading eigenvectors. These are our principal components, and the eigenvalues corresponding to these eigenvectors are the scale components. And of course, the PCA is unsupervised procedure in a sense that it does not require us to write down a factor model. If we have a factor model, we can show that the sample covariance matrix in the two-dimensional case can be written as this lower n component, which is obtained from the product of loadings times loadings transpose plus some extra terms, which is a noise. And so if this noise is sufficiently small, this suggests that we can identify loadings by looking at the leading eigenvectors of the sample covariance matrix. So the loadings lambda for the factor model estimated with the PCA would be the first R eigenvectors of the sample covariance matrix YY transpose. And now we can also apply this procedure to identify factors and loadings in the tensor factor model. To do that, we will consider unfoldings. So we will metricize the tensor, and tensor metricization or unfolding is an operation that kind of generalizes vectorization of matrices. And if you have a three-dimensional tensor, so here we have a tensor that has dimensions 3, 4, and 2. So this three-dimensional tensor can be unfolded or matricized in 3 different directions. So we can take these slices one by one, row by row, and put them together into one long matrix. We can also take this slice, and then column by column, and we put them together in this matrix. And we can take columns of this tensor, and we can put them together and get the third metricization. So then the idea would be to apply the PCA to each of these 3 unfoldings or metricizations. So let's look at the first metricization. So this is a 3-dimensional tensor factor model. We have a tensor of dimensions n times j times t. We have vectors of loadings lambda, mu, and a vector of vectors f, and sigma is the scale component. So what we will do, we will take slices corresponding to a cross-section of dimension n, and we will put them all together. So we are basically pulling the time series dimension with this other dimension where we have j dimension. And so if you do that, we get the matrix of loadings here in front of the other matrix. And so this suggests that if you look at the sample covariance matrix using this metricization, perhaps we can identify the matrix of loadings lambda. So this lambda basically collects all R loadings corresponding to different factors together, observed for all n cross-sectional units. And in this second matrix that we have in the product, we have this notation. So this denotes the Hartree-Rao product, which is defined as a column-wise Kronecker product for two matrices. So this is tensor product with subscript k is a Kronecker product. And the Hartree-Rao product is taking columns of two matrices and multiplying them in the Kronecker sense. So this was the matricization that corresponds to the first cross-sectional dimension, but we also have two other matricizations here. And these two other matricizations allow us to get the matrix of loadings corresponding to the second dimension of the tensor here in front. And the third matricization, it allows us to get the matrix of time series factors. So this is a T times R matrix in front of this equation. And then if you assume that factors and loadings are orthogonal, we can write the sample covariance matrix as loadings times the diagonal matrix with scale components times loadings transpose plus some noise. And so this tells us that we can identify loadings corresponding to the first dimension by looking at the eigendecomposition of the sample covariance matrix that we get from the matricization in the first dimension. So in this way, we get three PCA estimators. And the complete procedure will be described later. So here we have the same idea generalized to d-dimensional tensors. In order to identify factors or loadings, so here Mj will denote either a factor or a loading, depending on which of the dimensions J corresponds to. And so one of these n's will be the time series dimension, and the other n's will correspond to heterogeneous loadings. So these are dimensions for cross-section and these extra dimensions that we get in the tensor. And so this d-dimensional tensor can be metricized in d different ways, where we pull in one of the dimensions in front, and we are pulling all other dimensions together. And if you do that, we get a matrix of factors or loadings in front of this matrix. And we can apply PCA to the sample covariance matrix to get the first R eigenvectors. So this is the complete procedure, Tensor PCA algorithm, as we call it. For every dimension J, we will unfold the tensor. We will get factors and loadings denoted, factors or loadings denoted by Mj as the leading R eigenvectors of the sample covariance matrix. And then we will estimate the scale components taking the square root of eigenvalues of these metrics. So next, I will present some supporting asymptotic theory for this procedure. So first, we want to understand how these tensor dimensions help us to estimate factors and loadings more accurately. So under some regularity conditions, if you assume that factors and loadings are orthogonal, if you assume that errors are IID, we can relax that condition. And if you assume that we have the finite force moment for errors, then we can get the following rate for the L2 norm of the estimation error. So again, this Mj can be a vector of factors or a vector of loadings corresponding to each dimensions. So here in this rate, we see that we get tensor dimensions. So nj corresponds to the dimension of this vector, and then the product of all other dimensions. We also get the sum of scale components, and we also get in the denominator the eigengap. This eigengap sigma is basically a measure of the factor strengths. So if we estimate R's vector, this delta R would be the eigengap, the distance to the closest eigenvalue or the closest scale component to factor R. So next, in order to get more tractable results, we will make the strong tensor factor model assumption. So this assumption, we generalize this assumption from the usual strong factor model in the two-dimensional case. And the assumption tells us that if we take the product of scale components and divide them by the product of dimensions, in the limit, this converges to some constant dr. And we have R such constants. They have to be distinct because we want to identify factors, and they have also to be strictly positive. So this assumption is sometimes critical, but if you have a model with random factors and loadings, it can be justified by the strong law of large numbers. So this assumption is only critical if you talk about the factor model where loadings are not random, where loadings are deterministic. Because in that case, it could be the case that loadings are very small, and so this makes the problem of identifying factors very difficult if you have very, very, very small loadings.
I interrupt exactly on this, Andrii. So this means that a case where you only have, let's say, two panels n by t, you stack one below each other. So I'm matricizing this tensor in this way. And let's say that I have a degenerate factor model where I only have a pervasive factor in the first panel and no pervasive factor in the second panel. So this assumption is ruling out this extreme case.
So if you take a two-dimensional factor model, yes, with two factors.
No, I'm thinking about two panels, which would be the third dimension, if you want. But I only have a pervasive factor in one panel and not in the other. So this assumption is ruling out this case. Is this correct or not? So,
okay. So yes, that's a good question. So if you have, for example, a three-dimensional tensor and we put it as a sequence of panels, this assumption is kind of common to all panels. So we have the same factor strengths no matter which matricizations we consider. And it's going to be a product of norms, of loadings and factors. So if you just have a two-dimensional factor model, this sigma would correspond to the norm of factor times the norm of the loading, and so norm squared. And so if we write the norm explicitly, this would be just the average factor and the average loading squared. And so by the strong law of large numbers, we know that it would converge to some positive constant. But if you have deterministic loadings, we can pick up sequences where this can be violated. But yes, so a short answer to your question, yes. So we would have the same measure sigma, no matter which matricizations we look at. So it corresponds to a factor, not to the matricization, at least in the population. Yes, so that's a good question. Okay, so if we make this strong factor, or as Mirco referred, pervasive factor model assumption, then we can get some simplifications for these results. For this result, and we can see that the estimation error in the L2 norm would basically be driven by the product of all other tensor dimensions. So having extra tensor dimensions allow us to estimate factors and loadings more precisely, because we can explore the variation that we have in the data along these other dimensions. So next, we also have the asymptotic distribution for inner products of factors and loadings with some vector denoted by nu. And for example, we can pick a vector which has all entries equal to 0 and one entry equal to 1, in which case the inner product would be just looking at a loading for a specific cross-sectional unit or a factor at some particular point of time. But we can have some other inner products. For example, if you have nu equal to 1 over nj at all entries, we would take the average factors or average loadings. And so we have the distributional, the asymptotic distribution for these inner products, where the convergence rate would be, the normalizing sequence would be the product of the square root of all dimensions except for the dimension j. So the dimension j is the one for which we estimate the factor or the loading. And we get this asymptotic variance, which is kind of similar to what we get to the PCA, but it's slightly different because we have the factor structure. Next, we also develop a formal statistical test for the number of factors. So to the best of our knowledge, currently there are no formal tests in the statistical literature for tensor factor models. And here we build on the eigenvalue ratio statistics by Onatsky in Econometrica. So the null is that we have at most little k factors. The alternative is that we have more than little k, but less than large k factors. And the idea of this test is to use the eigenvalues and try to detect sharp changes in eigenvalues. So we could take, for example, the difference of consecutive eigenvalues, look at the scree plot. If you see a huge jump, this means that probably we have this number of factors. So the reason why we look at differences and ratios is that typically here we have a random matrix asymptotics because all dimensions grow at the same time, and we have some non-standard distributions with unknown scale and location parameter. And so the difference and the ratio allows us to get rid of these unknown location and scale parameters. So we follow this idea. And in our case, we would get d different test statistics for each of the matricizations. And we can show that under the null hypothesis, the distribution of these statistics can be approximated by the max of the ratio of differences of Tracy-Widom type 1 distributions using the random matrix asymptotics. So this is under the null. Under the alternative, it diverges. And so we end up having d different statistics for the same null hypothesis from different matricizations. We don't know the joint distribution, so the idea would be to combine p-values from these matricizations. So we can take the average p-value, the smallest p-value, or the largest p-value with an appropriate adjustment factor to make sure that we are getting a p-value. And these adjustment factors are discussed in particular in a paper by Wong and Wang. The distribution that we are getting is non-standard, but we can simulate it using computer, and so we have to look at the right tail of this distribution for the critical value. So next, if there are no questions on the asymptotic theory, I'll move to Monte Carlo simulations and empirical application. No questions. Okay, good. So Monte Carlo experiments. So in Monte Carlo experiments, we want to do two things. First, we want to verify that the asymptotic distribution theory works. So the asymptotic theory works. And second, we also want to understand how beneficial to take into account these tensor dimensions is. So, for example, if you look at the three-dimensional tensor factor model, what we could do, we could just pull these two loadings, the loading corresponding to the cross-section I and the loading corresponding to the other dimension j. We could pull them together, and we could just ignore the fact that we have tensor structure and just apply PCA to that. The drawback of doing that is that we have to feed more parameters. So here this pooled loading beta ij is of dimension n times j, and we also have to feed factors. So we feed nj plus t times the number of factor parameters. On the other hand, if you use the tensor factor structure, we are identifying separately the loadings corresponding to cross-section and loadings corresponding to this other dimension. And so we have to feed r times n plus j times plus t parameters. So we have an improvement in the number of parameters that we are feeding. And it's usually a good idea to feed models with smaller number of parameters, as we know. So in this table, we are looking at the model complexity, and we compare the tensor approach to this naive pooling, where we ignore the tensor structure. And we look at the ratio of the number of parameters to the sample size for different values of the sample size and different number of factors. So what we see here is that tensor approach gives us less complex models. So sometimes the improvement in the ratio of parameters to the sample size is by more than a factor of 10. For example, here and here, we get an improvement by a factor of almost 40. So we have a small number of parameters that we need to feed for fixed sample size, and so we can expect to get better results. We can expect that we would estimate factors and loadings more precisely if you use the tensor dimension. So for the Monte Carlo experiments, we consider the following DGP. The factor is autoregressive with autoregressive parameter 0.5. We have a normal distribution for factor errors and for the tensor factor model. And we define the signal strengths as follows. So this corresponds to the strong factor model assumption. We consider the cases where we have 5 factors, and the tensor dimensions are 100 time series data points, 30 cross-sectional data points, and 20 data points corresponding to the third dimension. So first, in simulations, we will look at how well the model fits the data. And here, blue curve is what we get with our approach, and the red curve is what we get with the naive pooling approach. So what we see here is that for a fixed number of parameters, our model feeds the data much better. So with naive pooling, we have just one factor corresponding to this number of parameters, and we get R squared, which is 0.45. While in our case, for this fixed number of parameters, with a model with 5 factors, we are getting R squared, which is pretty close to 1. How do we feed the model in practice? So there is large literature in the tensor decomposition, numerical tensor decomposition, and what people are doing there, they are trying to obtain the low rank approximation to the observed tensor. So we take this rank R approximation, and we want to solve the problem over loadings, lambda and mu, and factors f, and we want to get as close as possible in some norm, for example, Frobenius norm. So the problem with this approach is that we are trying to fit a non-convex, we are trying to solve the non-convex optimization problem. So we have to solve this problem jointly for loadings lambda, loadings mu, and factors f. And because of non-convexity, we may get a solution that is sensitive to the initial starting values. We're also going to get different factors and loadings for different rank that we specify in this problem. And usually people solve this problem using what is called the alternating least squares algorithm. So the idea would be to fix 2 dimensions and solve over 1 dimension, and then rotate this dimension until we get some convergence. So we solve it sequentially. We pick some starting values, we fix mu and f, we solve for lambda. Then we use that lambda that we fitted in the previous step, and we solve for mu. And then we solve for f. And then we update these values and we rotate it again until we get convergence to something. So in these simulations, we will compare this ALS procedure to our Tensor PCA, where we don't have to solve any non-convex optimization problems. We just can use the spectral decomposition, eigenvalues and eigenvectors. We allow for a different number of factors, 1, 2, 3, 4. And we will fit a one-factor model without the knowledge of true factor. And we will measure the estimation accuracy using L2 errors. So the top graph shows us estimation errors, the distribution of estimation errors for one-factor model. The bottom is for two-factor model. Blue is Tensor PCA, and orange is Tensor PCA, and blue is the ALS algorithm. So what we see is that sometimes the ALS algorithm fails. So we get this right tail in the distribution of errors. Sometimes we are getting large errors. And this problem becomes more and more severe if we have more factors. So with 2 factors, we have this larger concentration of errors, larger part in the distribution. So we get these large errors. With 3 factors, we fail to find the right factors and loadings even more frequently with the ALS. 4 factors, even more. So next, we would like to look whether our convergence rates can be confirmed by Monte Carlo simulations. So this is the convergence rate that we got for factors or loadings. And the rate would be 1 over square root of JT when we fit the cross-sectional loading lambda, 1 over square root of NT if we fit a loading mu, and for the factor, we would get 1 over the square root of NJ. So we'll consider a model with 1 factor with these signal strengths, and we will look at the baseline model where the time series is 100, and the cross-section is 30, and the other dimension is 20. And we will look at 3 deviations from the baseline. First, we will double all dimensions. Second, we will double only 2 dimensions. And third, we will double only one of the 3 dimensions. And we use the same L2 errors to measure the performance. So first, what happens if you double all dimensions? In that case, we see that the error reduces. So the distribution of errors, blue is the baseline, moves to orange. And it's reduced on average by a factor of 1/2, which is what we would expect from these rates when we double 2 dimensions. When we double all dimensions. If you double only 2 dimensions, only n and j, we expect that the accuracy for lambda and mu would be improved by a factor 1/√2, and for f, we expect that the error would reduce by 1/2. And we can also see this on this graph. And now we double only n, and in that case, we expect no improvements for lambda, and we expect that errors for mu and f would be reduced by a factor of 1/√2. And we kind of see it here. There are no improvements for lambda, and we get roughly, on average, 1/√2 improvement for mu and for factors f. So next, we would like to look at how the eigenvalue ratio test performs. So just to recall, the null is that we have at most k factors. Here we consider the null that we have 1 factor, and the alternative is that we have more than 1 factor, but less than large k factors. And the scale component, the signal for each factor is computed like this in simulations. So for the second factor, we will start with a signal which is equal to 0, and we will look at what happens when we move away from the null hypothesis, when the second factor becomes stronger and stronger. And we can apply the test as I discussed. In the 5-dimensional case, we can apply it to each of the 5 dimensions, and so we'll get 5 different test statistics. And we will compare p-value combinations from a paper by Vogue and Wang 2020. So first, we look at a single matricization, and we look at power curves. So we see that the test is consistent as the strength of the second factor increases. We get power that goes to 1. We also control the size, and we explore how sensitive the test is to the upper bound on the number of factors. So we kind of see that if you have a better upper bound on the possible number of factors, we get slightly more powerful test. But it works in all cases. Next, we look at the 5-dimensional tensor. And in the left picture, we look at power curves corresponding to tests of different matricizations. So we have 5 different matricizations, and we also plot the result for the minimum p-value combination. So we see that the minimum performs quite well. Some matricizations have lower power, some have slightly higher, but the minimum performs quite well. And we also compare these other p-value combinations, the max of p-value, the mean, the median, and the minimum. And what we find here is that the mean controls the size relatively well and has slightly higher power. Other p-value combinations, they are more conservative. So we don't control the size of the test well with other matricizations, but we get good power. So these are results for Gaussian errors, and we get similar results for student T errors. Okay, so that's it for Monte Carlo simulations, and the last part of the presentation is the empirical application to asset pricing, namely sorted portfolios. So just to recall, the classical asset pricing model is the capital asset pricing model, where we are trying to explain the excess returns using the market factor, and we have some loadings for different assets. And we have the individual asset risk premium, which is compensated on its association with the market risk premium. So this model has been extended to a multiple factor model. For example, the Fama-French three-factor model includes what they call a small minus big factor and a high minus low factor on top of the market factor. And there are two more factors in the five-factor model. And then the empirical finance literature discovered hundreds of such factors or anomalies that can explain excess returns. So this is called factor zoo. There are hundreds of new factors discovered in the literature. How these factors are usually constructed? They are constructed by doing sorting on some observed characteristics. So for example, as MB is small minus b, to construct that factor, we sort on the firm size, and we take small minus large sorted portfolios. So a paper by Letau and Palgar uses 37 of these characteristic sorted portfolios from the factor zoo and extracts systemic factors using the PCA. So this ignores the tensor dimension, and this corresponds to what we call pooling two-dimensional factor model. So we only explore pooled loadings in this way. And we discussed two issues with this approach. First, the model is overparameterized. And second, we cannot identify loadings specific to different deciles and different characteristics. We can only identify pooled loadings. So let's look at the three-dimensional factor model for this data set. So YIJT here is the excess return for a portfolio sorted on ICE characteristic, and we have J's quantile at time t. In the pooled two-dimensional approach, we say that these loadings are just a beta, and we are estimating these betas. We used a data set from a paper by Zheng and Zimmerman. So this is an open source database. It's publicly available. And in this data, we cover 30 years from 1990 to 2020. These are monthly returns sorted, and we look at portfolio sorted into 10 deciles based on different characteristics. And in this factor zoo, we have 133 of such characteristics. So we end up working with a three-dimensional tensor that has 133 characteristics, J deciles, and 360 time periods corresponding to monthly returns. So this gives us roughly over 500,000 of observations in this tensor. And so we will compare the estimates that we are getting with our Tensor PCA approach to the alternating least squares algorithm. So first, we look at loadings that are specific to characteristics. And we have Tensor PCA at top and alternating least squares at the bottom. So the first factor is expected to be the market factor. And we see that loadings for the market factor are always positive. If you use the Tensor PCA approach, if you use ALS, sometimes we get negative loadings. So that's probably the case when the ALS cannot recover the global optimum. For the second factor, in our Tensor PCA approach, we get roughly 50%, 50-60% of positive loadings. For ALS, we mostly get positive loadings. And we also report highest to lowest characteristic loadings when we use the Tensor PCA approach. So we can see that the largest loadings for the market factor correspond to factors like firm age momentum, idiosyncratic risk, and price. And for the second factor, we get beta-ask spread, KPM, beta, and idiosyncratic risk. So these are three largest loadings for these three factors. And these are the smallest loadings. So these are factors with the smallest loadings. Next, we look at loadings that we have specific to each decile. So this is this third tensor dimension. If you look at the first loading, we kind of see a pattern where the loading decreases up to the middle decile, and then it starts increasing if you use the Tensor PCA. For ALS, we see the same pattern, but we have less symmetry across different deciles. And for the second factor, we see that the loadings are monotonically decreasing or increasing. So there is a sign indeterminacy here. So if we flip the sign, we get a similar pattern. And so next, we will consider high minus low portfolios. So these are portfolios constructed by taking the difference of extreme deciles. So we take 10th decile and subtract the first decile for portfolio returns. And so what this does, it basically collapses this three-dimensional tensor to a two-dimensional panel data set. And if you just write the difference mechanically, we get this equation. And what we have seen for the Tensor PCA, we have seen that the loadings corresponding to the 10th decile and the first decile are very close to each other, which means that when we take the difference, they kind of cancel out. And so this tells us that the risk premium associated with characteristics are driven mostly by systemic factors that we have beyond the market factor. So the market factor kind of cancels out. And we can also see that the high minus low portfolios give us the highest risk premium associated with a single characteristic. So we get better results when we look at 10 minus 1 compared to 9 minus 2 or 8 minus 3. So this kind of confirms that it makes sense to construct factors by looking at the difference of extreme deciles. So to conclude, in this paper, we consider a d-dimensional tensor factor model that is estimated with the PCA. The advantage of this approach is that we get closed form expressions, and we don't have to solve a non-convex optimization problem. So we can just use PCA routines. We have some asymptotic theory that tells us how tensor dimensions can improve the estimation accuracy of factors and loadings. And we introduced the first the first formal statistical test for the number of factors in the tensor factor model. And the test is based on the eigenvalue ratio statistics, as well as p-value combinations across different unfoldings. And we consider an empirical application to sorted portfolios. And so we see that the Tensor PCA gives us results that are more reasonable and more in line with high minus low risk premium calculations as opposed to the ALS algorithm. Thank you.
Thank you very much for an interesting paper. We can now stop the recording and move to the chat if anyone has questions. Thank you.
Great talk, Andrii.